Thank you for joining us this morning on our webinar on RTDs, thermocouples and thermistors. It's roughly about 15 minutes, and as always, if you have any questions, you can put them in the questions panel at any point throughout the video and we'll get to them at the end. So we'll get going.
Welcome to today's tutorial. Let's get started. Today we will be discussing thermocouples, RTDs, and thermistors, and how they integrate with Horner's all-in-one controllers. We will demonstrate how to configure and wire a Horner OCS for each sensor type. And as always, we'll finish with a live Q&A session. Let's start with thermocouples. Thermocouples work based on the material properties of metals, where if you join two metals at one point, that point will generate a small voltage that is proportional to temperature. Thermocouples are one of the most popular temperature sensors in use. Let's discuss their advantages and disadvantages. While they're relatively inexpensive and have been in use for years, they support the widest temperature range of any commonly used sensor. However, they can be a little bit tricky to work with, and they're also susceptible to electrical noise, so you have to be careful with your installation. If we look at this voltage versus temperature curve, we've got many types of thermocouple listed. When you have a different combination of metals, you have a different type of thermocouple. Different types have been created for different applications, some for really hot applications, or nuclear applications, etc. Some of these curves are very shallow, and you don't have a large millivolt difference to represent a difference in temperature. That's why different thermocouples are supported for different applications. How would we connect a thermocouple to a PLC or to a Horner all-in-one controller's I/O? Well, we take a thermocouple probe and we would connect it to the terminal strip on the I/O block and measure the voltage. It seems simple, right? The problem is, when you connect metal A to the plated metal on the terminal strip, you have the thermocouple effect of metals, where a small voltage is generated depending on the temperature of the terminal strip. That's called cold junction compensation error. The cold junction is where we connect our instrumentation in our I/O module. The hot junction is where we do our measurement for the actual temperature. With cold junction compensation, we have to measure the temperature of the cold junction terminals, and based on the thermocouple type that's in use, we predict the voltage loss at that temperature at each terminal. Then we subtract that from the total voltage, and we have the resulting voltage at the hot junction. We convert that voltage to temperature with a lookup table or a polynomial, and we get our temperature. If the hot junction that you're measuring is not insulated electrically from the metal sheath in which it's installed, then it's a grounded thermocouple. If the sheath is insulated from the hot junction from the metal tip, then it's an ungrounded thermocouple. Because the voltages are so small and they can be susceptible to noise, it's important to look out for grounded versus ungrounded thermocouples. Not all instrumentation supports both types. At Horner, we have some I/O options that support grounded thermocouples, and we have some that don't. The XL Model 5 and SmartBlock support both. The XL Model 6 and SmartRail only support ungrounded. If you buy a thermocouple probe, it's going to come with maybe a meter or two of actual wire, and that's not going to reach your I/O module on the back of your controller. You need to extend it using thermocouple extension wire. If you decide to have extra terminal blocks in the signal path, then make sure that every intermediate connection uses special thermocouple type connections. Make sure there's no crazy temperature gradients along that extension wire, as they will cause inaccuracies. There are different colors on the positive wire for each thermocouple type. However, the red wire on all different thermocouple types is negative. Now let's talk about RTDs and how they work. RTD stands for Resistance Temperature Detector. The resistance of the sensor changes with temperature. Let's discuss the advantages and disadvantages of RTDs. RTDs are accurate and pretty easy to work with. They can be expensive, but there are many good quality RTDs at a regular price. They also don't have the extended temperature range that a thermocouple has. RTDs are the most popular sensor type among our customers. Just like with thermocouples, you have different types of RTDs. The most popular is PT100, which stands for Platinum 100 Ohm. If you're looking at multiple options for Platinum 100 Ohm, you want to use the DIN standard, which has a temperature coefficient of 0.00385. There are many others, but PT100 is by far the most popular choice. If we look at resistance versus temperature, we've got around a 1000 degree range for RTDs. Over that range, you've got about a 400 ohm variation in resistance. We have an RTD where we're measuring temperatures around freezing. If we're measuring temperatures in the ambient range or colder, we're looking at 100 ohms as the value of the RTD sensor. If we have 2 or 3 ohms of wire resistance between the probe and the I/O module, there may be a degree or two of error. While you don't have cold junction compensation with RTDs, you do have lead wire compensation. So what is lead wire compensation? RTDs are sold in either 3-wire or 4-wire versions. I'm showing a 3-wire version here. A 3-wire RTD contains an extra wire, the instrumentation, which the I/O module uses to send a small current down a signal path to determine the lead wire resistance. Once the resistance of the lead wire is calculated, then each wire is assumed to have the same resistance value, which is subtracted off. And now you're left with the actual resistance of the sensor itself, which you can convert to temperature using a lookup table or polynomial. The small current that is sent down the wire by the I/O module must be small to avoid self-heating. Here are some things to look out for with RTDs when you're installing them. Make sure you use 3-wire or 4-wire RTDs. Those are designed with quality in mind and will eliminate lead wire compensation. For our temperature measurement, we can use copper extension wire, but you should use 0.25 square millimeter or larger. It's critical that all extension wires are exactly the same length. If there's differences in the length of the extension wire, then you're going to get errors. And as a rule of thumb, you want to keep the wire length below 100 feet. The last temperature sensor we're going to look at today are thermistors. Thermistors vary their resistance with temperature, but the resistance values are higher. The advantages of thermistors are they're very easy to use and they're inexpensive. However, they're only good for ambient type temperatures, and their resolution varies with temperature, so they're not highly accurate, but they do a pretty good job in certain applications. So, with thermistors, the lead resistance of the wire connecting our probe to our module is not important. Thermistors are typically 2-wire devices, temperature range is quite narrow, and resolution changes significantly with temperature. You need to select the right type of thermistor, and there are a lot of different types. The types of thermistor that we support have a resistance of 10k ohms at 25 degrees Celsius, and they have a beta of 3574. The resistance to temperature conversion is currently done in logic. If you pick the right sensor, and you get the right conversion routine that we provide in our documentation copied into your logic, then you're smooth sailing. Now I'll demonstrate how to configure and wire a Horner OCS for each sensor type. I have an XLE Model 5 here. Now with the Model 5, the first 2 channels of analog support thermocouples, RTDs, 4 to 20 mA and 0 to 10 volts, with the default being 4 to 20 mA. If you want to change to thermocouple or RTD, then you have some jumpers that you need to move. The jumper for analog input channel 1 is here, and the jumper for analog input channel 2 is there. In this case, the default for both is set for 4 to 20 mA. If we look up the documentation, which I won't show here, you'll see that if you want to support thermocouple, these 2 jumpers need to move to the bottom. So all 4 jumpers are at the bottom for thermocouple. If you want to support RTD, you move these 2 jumpers up. So all 4 jumpers are at the top for RTD. You'll notice this bar here at the bottom that seems to be epoxied to the terminal strip. That's an isothermal bar. Underneath that is a temperature sensor, and that thermal bar is bonded with the terminal strip. So if we're measuring thermocouples, we can do cold junction compensation properly. Okay, so that was the Model 5. Now I'll show you the Model 6. This time, I'll show it in the back of a 6-inch unit. You'll notice that there are no jumpers, there's just a header for expanding I/O internally. You'll also notice that there's no isothermal bar. That's because we're using tiny temperature sensors located at the appropriate points on the terminal strip where thermocouples might be connected. So we're still doing cold junction compensation. The Model 6 has some pretty fine terminals on here. There are so many terminals because the Model 6 supports 12 in and 12 out, digital 6 in and analog 4 out thermocouple. And each analog input has at least 3 terminals because it can be used with thermocouples and RTDs, in addition to voltage and current. Now let's jump into some Cscape configuration. I'm going to pull up the hardware configuration option in Cscape. Alright, what I have here is an XL4 Model 5, and I'm going to configure channel 1 for a thermocouple. So I'll go under local I/O, then config, and then module setup. Under analog in, I have 2 channels. Whenever the Model 5 has 2 analog input channels, default is 4 to 20 mA. But if I want it to be a thermocouple, I'll move the jumpers as appropriate and then select the thermocouple type from this list. So let's say I select K-type thermocouple. It specifies 1/20 with degrees Celsius as the units that will be reported through the analog input register. I will do the same thing with channel 2. The channels can be completely independent. I can make it whatever I want, but I'll set another K-type thermocouple here. We also have a filter constant. I typically recommend you set the filter constant to a value of at least 3, unless you're looking for extreme speed. Thermocouples have a very low signal and are somewhat susceptible to noise and transients, so this filter value can be set anywhere between 0 and 7 to filter that noise. So that's how I would configure a Model 5. The temperature values are coming back in 120 degrees Celsius increments. If I wanted to see those degrees in Fahrenheit, I would take the raw analog input value that comes in as an integer. I'd convert that to a real value and store it in a variable that I've called tcreal. And then I'd do a math expression, where I'd take the 20th degree increments, multiply by 20 to get 1 degree Celsius, and then, using that, do the standard degrees Celsius to degrees Fahrenheit conversion, which is multiplying it by 1.8 and then adding 32. So that's a simple way of doing the conversion from Celsius to Fahrenheit. Now let's look at the Model 6 configuration. So I'm going to select the Model 6 here. I'll then go back to the local I/O tab, then go to config, then module setup, and analog in. Okay, it's very similar but a little bit different. You have a few more types available. We have PT1000 curve here, which I'll select. The filter constant is available on a per channel basis, and you can choose whether you want to report in degrees Celsius or Fahrenheit. We also report it in 10th of degree increments instead of 20th of a degree increments. Lastly, I'll show you an example program for thermistors, so let me pull that up here. Okay, now this looks a little bit complicated, but it's not really. At the beginning, it's moving constant tables into specific locations that are doing part of the conversion process. So each of these are for 2 channels, and these values from the concept table are in the thermistor supplement documentation. Basically, it's using these values as a reference to calculate the thermistor curve within the 0 to 10 volt signal. For the hardware configuration, you need to set the analog inputs to 0 to 10 volt. If you click under the local I/O, then type 2, module setup, analog in, you'll see that for thermistors, we've set them up for 0 to 10 volts. If you set these to 0 to 10 volts, and then you execute these polynomials which we've given you, then it's going to give you the appropriate temperature for each channel. This is example code that you can get from Horner, and there's a complete write-up on it. We've also got documents detailing all of the steps in converting from voltage if you're using thermistors. Thermistors are available for the Model 2, 3, and 4. The Model 2 has 12 digital in, 6 relay out, and 4 analog in. With the Model 2, you can get 2 of the 4 channels converted to thermistor at the factory, or 4 of the 4 channels converted to thermistor at the factory. The Model 3 and the Model 4 I/O options have 2 analog input channels each, and if you get the thermistor option, both channels are configured for thermistors. So that wraps up our demonstration for today. Thank you for attending today's tutorial. The Q&A session will begin shortly.
Okay, let's see if we have any questions in. Do we have wiring diagrams for different RTDs? I presume you mean different amount of wiring versions. Yes, on the data sheet of the unit you have that supports RTDs, that will be found there. Temperature ranges, again, on the data sheet, it'll specify the temperature ranges that are supported. Don't see anything else just now. So I will take us to the screen again. Okay, hopefully you can all see my screen there now. So next week we do have connecting encoders to the Horner OCS. And in the following weeks again, we have security and getting started with AC. So all the registration links are there as always, so you can register now if you wish. We've seen that some of you have already, which is great. And if there's any bits of this or any other past video you want to go back and watch, we do put all our past webinars up below here. So today's one should be up either today or tomorrow. Okay, still no other questions in. Okay, thank you for joining us this morning. We'll leave it there and hopefully see you again.